Hello all, welcome to online lecture series on Laplace transforms. In the last lecture, we learned what is an unit step function or Heaviside function and we derived Laplace transform of that unit step function. Let us recall the definition of this unit step function and what is Laplace transform of unit step function. Unit step function is denoted by u of t or h of t and it is defined as u of t is equals to 0 if t is less than 0 and 1 for t greater than or equal to 0. We can define the unit step function at t is equals to a as u of t minus a is equals to 0 for t less than a and 1 for t greater than or equals to a. And the Laplace transform of unit step function is L of u of t minus a is e power minus as by s. Then we derived second shift property for Laplace transforms which states like this. If g of t is defined as f of t minus a for t greater than or equal to a and 0 for t less than a, then the Laplace transform of g of t is nothing but e power minus as into Laplace transform of f of t. We can state second shift theorem in another form, that is L of f of t minus a into u of t minus a. U of t minus a is unit step function here. So the Laplace transform of f of t minus a into u of t minus a is e power minus as into Laplace transform of f of t. These both are same equivalent statements because g of t can be expressed as f of t minus a into u of t minus a. So keep in mind these two statements. One thing is if g of t is defined like this, then according to second shift theorem, Laplace transform of g of t is e power minus as into L of f of t, where we can obtain f of t from here. We'll have f of t minus a here and from this we can guess what is f of t. And when the function is of the form f of t minus a into u of t minus a, to find its Laplace transform, we use this form of second shift theorem. Okay, so now let us go to some problems where we apply the second shift theorem to evaluate Laplace transform of some functions. The first function here is g of t is equals to cos of t minus pi by 3 for t greater than or equal to pi by 3 and 0 for t less than pi by 3. Now this g of t resembles f of t minus a for t greater than or equal to a and 0 for t less than a. So to find Laplace transform of this g of t, we can apply second shift theorem. For that, first we need to write what is f of t. Here we have cos of t minus pi by 3. Compare this with f of t minus a. So in place of a we have pi by 3 and in place of f of t we have cos t. So first we identify what is f of t. In this case f of t is cos t. Now first let us find what is Laplace transform of f of t, that is Laplace of cos t, which is s by s square plus 1. Now let us apply second shift property which states that L of g of t, when g of t is defined like this, is equal to e power minus as into L of f of t. Here a is equals to pi by 3. Therefore, if we apply this property, we get L of g of t is equals to e power minus a is pi by 3s into L of f of t, which is equals to L of f of t is s by s square plus 1. So Laplace transform of g of t is e power minus pi by 3s into s by s square plus 1. Now let us see another problem. Find the Laplace transform of the function t minus 2 whole cube into u of t minus 2. U of t minus 2 represents unit step function. So compare this function with the equation f of t minus a into u of t minus a. So that f of t minus a is t minus 2 whole cube. From that we identify what is f of t. Obviously f of t is t cube. So we use the second form of another form of second shift property here, that is L of f of t minus a into u of t minus a is e power minus as into L of f of t. So now we compare the function, the given function t minus 2 whole cube into u of t minus 2 with f of t minus a into u of t minus a. Then in place of f of t minus a we have t minus 2 whole cube, and in place of a we have 2 here. A is 2 and f of t is t cube, because f of t minus a is t minus 2 whole cube. F of t is equals to t cube. Now we'll find L of f of t, because we need L of f of t in the property here. L of f of t is L of t cube, and we know that L of t power n is n factorial by s power n plus 1. Therefore L of t cube is 3 factorial by s power 4, that is 6 by s power 4. So now according to the second shift property, L of t minus 2 whole cube into u of t minus 2 is equals to e power minus as. A is 2 here, therefore e power minus 2s into L of f of t, and L of f of t is 6 by s power 4. Therefore this is 6 times e power minus 2s by s power 4. Next we are asked to find the Laplace transform of e power minus 3t into u of t minus 2. So here we can apply second shift property, provided we have f of t minus a here. We have e power minus 3t into u of t minus 2. So here also if this function can be written as f of t minus 2, then we can apply second shift property. But here we have only t here, minus 3t. So to write it in terms of t minus 2, we add and subtract 2 to the exponential term. That is, the given function can be written as e power minus 3t minus 2 plus 2 into u of t minus 2. Now if we split e power t minus 2 plus 2, we get e power minus 3 into t minus 2 into e power minus 3 into 2, that is e power minus 6 into u of t minus 2. This e power minus 6 is constant term because it does not contain any t terms. So now Laplace transform of e power minus 3t into u of t minus 2 can be evaluated using second shift theorem. Now if we compare this function with f of t minus a into u of t minus a, we get a is equals to 2, and what is f of t? It is e power minus 3t, because f of t minus a is e power minus 3 into t minus 2. Therefore f of t is e power minus 3t. Now according to second shift property, now we find L of f of t before going to second shift property. L of f of t is L of e power minus 3t, and it is 1 by s plus 3. Now we will apply second shift property, which states L of f of t minus a into u of t minus a is e power minus as into L of f of t. Therefore L of e power minus 3t into u of t minus t, which is given as L of e power minus 6 into e power minus 3 into t minus 2 into u of t minus 2. E power minus 6 being constant can be taken outside the Laplace transform. So we have here L of f of t minus a into u of t minus a, but L of f of t minus a into u of t minus a is e power minus as into L of f of t. So this is e power a is 2, therefore this is e power minus 2s into L of f of t, and L of f of t is 1 by s plus 3, and e power minus 6 into e power minus 2s is e power minus 6 minus 2s. Therefore Laplace transform of given function is e power. If we take minus 2 common from this, we get e power minus 2 into s plus 3 by s plus 3. Okay. So now let us look into another problem where the function is f of t is defined as t for 0 less than t less than 1 and 0 for t greater than 1. We are asked to derive its Laplace transform. So now we consider the given function, and let us write it as f1 of t, where f1 of t is t in the interval 0 to 1, and f2 of t, that is 0, in the interval 1 to infinity. So if we remember, in the last lecture we made a note, if f of t is defined like this, then it can be written as f1 of t plus f2 of t minus f1 of t into u of t minus 1. You can go back to the last lecture, and if you want more clarity on this point, you can go back to last lecture. U of t minus 1 is unit step function at t is equals to 1. Therefore, now if we substitute here, what is f1 of t here? F1 of t is t. Therefore, t plus f2 of t is 0. So, 0 minus f1 of t is t into u of t minus 1. So, this is t minus t into u of t minus 1. Okay. Now, this can be written as, because we have u of t minus 1 here also we write in terms of t minus 1. For that we are subtracting 1 and adding 1. So that this becomes t minus 1 into u of t minus 1 plus 1 into u of t minus 1. So this is t minus 1 into u of t minus 1 minus u of t minus 1. Now to find Laplace transform of f of t, we apply Laplace on both sides. We know what is L of t, and for the second term Laplace of t minus 1 into u of t minus 1, we apply second shift property, and we also know the Laplace transform of u of t minus 1. So L of f of t is equals to L of t minus t minus 1 into u of t minus 1 minus u of t minus 1. If we use linear property of our Laplace transform, we get L of t minus L of t minus 1 into u of t minus 1 minus L of u of t minus 1. What is L of t? L of t is 1 by s square, and according to second shift property, second shift property is this: L of f of t minus a into u of t minus a is e power minus as into L of f of t. So in this case, t is equals to 1 here, and f of t is t, because f of t minus 1 is u of t f of t minus 1 is t minus 1 here. So e power minus s into L of t, and we know that Laplace transform of u of t minus a is e power minus as by s, and a is 1 here. Therefore, this is e power minus s by s, and hence Laplace of f of t, Laplace transform of f of t is 1 by s square minus e power minus s into L of t is 1 by s square minus e power minus s. So after simplification, we can write it as 1 by s square times 1 minus e power minus s into e power minus s. So these are some practice questions for you. Evaluate Laplace transform of g of t, where g of t is sine of t minus 3 pi by 4 for t greater than or equal to 3 pi by 4, and 0 for t less than 3 pi by 4. You can apply the first form of second shift theorem directly. And here we are asked to find Laplace of e power minus 2t minus u of t minus 1. So first you multiply e power minus 2t to both the terms, e power minus 2t into 1 minus e power minus 2t into u of t minus 1. For finding Laplace of e power minus 2t into u of t minus 1, you can apply second shift property, another form of second shift property. This is a function where you apply the second shift property, another form of second shift property directly. A is equal to 2 and f of t will be cos 4t. And finally you have L of e power t into u of t plus 3. Here we have, because we have t plus 3 here also we write in terms of t plus 3. That is, we write this as e power t plus 3 minus 3. That is e power t plus 3 into e power minus 3. Because e power minus 3 is constant, we can take outside, and we apply second shift property here, where a is equals to minus 3. Okay. So try these problems. In case you have any doubts, you can contact me. Thank you for watching the video.